the experiment that worked too well. At first, it felt like a triumph so complete that questioning it seemed unnecessary, almost ungrateful, because the experiment delivered exactly what it promised, and then continued delivering far beyond expectations. Results were clean, repeatable, and impressively consistent, the kind of outcome researchers dream about and industries rush to replicate. No alarms sounded, no warnings appeared, and success itself became the reason nobody looked closer. To understand why this experiment matters today, we need to examine how science interprets success. In laboratories, an experiment is judged by control, predictability, and reproducibility. If variables behave as expected and results scale cleanly, the experiment is considered solved. Success becomes closure. Funding moves on. Attention shifts elsewhere. But chemistry does not recognize closure. It only recognizes continuation. Modern systems are built on experiments that worked, materials that performed, processes that scaled, reactions that behaved exactly as designed. Once proven reliable, they are embedded into manufacturing, medicine, agriculture, and energy. What begins as an experiment becomes infrastructure, and infrastructure is rarely questioned once it works. This experiment followed that exact trajectory. In controlled conditions, it exceeded expectations. Efficiency improved dramatically. Waste dropped. Output stabilized. The reaction was elegant, almost beautiful in its simplicity. Researchers celebrated because complexity had been reduced to something manageable. A chemical process had finally behaved. This is the first narrative beat. A system that worked so well it inspired confidence instead of caution. Every replication reinforced belief. Every successful trial narrowed curiosity. The experiment was no longer examined for limits. It was treated as finished. The second beat followed with expansion. The experiment left the lab. It entered real environments, different temperatures, different scales, different stresses, but the chemistry still held. Performance remained strong. Small deviations were corrected easily. Nothing broke. Nothing resisted. The experiment appeared universally robust. That apparent robustness hid something important. The experiment worked by amplifying a single pathway. All other reactions were suppressed. Side processes were minimized. This made the system efficient, but it also made it narrow. All success flowed through one chemical route, and that route became dependency. The third beat formed quietly. As the experiment scaled, it began shaping its environment. Inputs adjusted to suit it. Systems reorganized around it. Alternatives disappeared. The experiment stopped being one option among many. It became the only option that made sense. And once that happens, failure becomes unthinkable. This is where the story begins to tighten. Because chemistry never promises that one pathway will remain favorable forever. Conditions drift, materials age, environments change. And when a system is built entirely around what works best today, it becomes exquisitely vulnerable to what changes tomorrow. The experiment worked too well. And that success is exactly what made the consequences impossible. To ignore once chemistry decided it was time to move on. As the experiment expanded beyond its original boundaries, chemistry began doing what it always does when given time, scale, and repetition. It started revealing side effects that success had carefully hidden. Not failures, not malfunctions, but consequences that only appear when a reaction becomes dominant instead of exceptional. The experiment did not break. It reshaped everything around it. At first, the system adapted smoothly. Inputs were optimized to feed the reaction. Supporting processes were trimmed away as unnecessary. Redundancy was removed in the name of efficiency. The chemistry became cleaner, narrower, and more focused than ever before. From a performance standpoint, this was ideal. From a resilience standpoint, it was dangerous. This is where the reveal deepens. By working so well, the experiment eliminated alternatives. Backup pathways disappeared because they were slower. Competing reactions were abandoned because they were less efficient. Over time, the system forgot how to function without this one perfect process. Chemistry was no longer one contributor among many. It became the backbone. As scale increased, the reaction began influencing conditions upstream. Raw materials were processed differently to suit it. Temperatures and pressures were standardized around its needs. Even environmental conditions were modified to maintain peak performance. The experiment stopped adapting to the world. The world adapted to the experiment. And chemistry took note. The early conflict forms here, because a system built around a single optimal pathway becomes hypersensitive to change. Small fluctuations that once meant nothing now matter. A slight impurity alters kinetics. A minor temperature drift shifts reaction balance. A delayed input creates cascading inefficiencies. The experiment still works, but only within a shrinking window. What nobody expected was how quietly fragility set in. There was no dramatic warning, no catastrophic signal, just increasing effort required to maintain the same results. More control, more monitoring, more intervention. Success demanded constant attention. The chemistry was no longer effortless. As engineers pushed harder to preserve performance, they unknowingly amplified risk. Controls tightened, margins narrowed, tolerance disappeared. The reaction was forced to remain perfect. But chemistry does not stay perfect under pressure. It responds by finding new pathways, often unwanted ones. This is where tension grows heavier. Because the experiment had become essential, entire systems depended on it functioning exactly as before. Questioning it now felt like threatening stability itself. So concerns were deferred, adjustments were made, and chemistry continued adapting in the background. The experiment was still working. That was the problem. Because as long as output remained high, the underlying shift went unnoticed. Chemistry was no longer cooperating. It was complying under constraint. And compliance, when forced, always has a limit. This stage sets the direction of the story. Because once a system relies completely on what works best, it loses the ability to survive what works differently. And chemistry never stops changing the conditions that define success. This is where the conflict finally becomes visible, not because the experiment fails outright, but because it begins demanding more and more effort simply to remain stable, revealing that success has quietly transformed into dependence. What once ran smoothly now requires constant calibration, constant oversight, and constant correction, as if the chemistry itself is pushing back against being held in one narrow configuration for too long. As conditions drift, even slightly, the reaction responds disproportionately. Small impurities that were once irrelevant begin redirecting reaction pathways. Minor temperature variations create uneven kinetics across the system. Localized stresses emerge where uniformity was assumed. The experiment still functions, but only through continuous intervention. Chemistry has stopped self-regulating. This is the core conflict. The experiment worked by suppressing complexity, but complexity never disappears. It waits, and once the system grows large enough, suppressed pathways begin reasserting themselves. Side reactions return. Byproducts accumulate. Efficiency erodes from the inside. The very mechanisms that once made the experiment elegant now make it brittle. The buildup intensifies as redundancy vanishes. There are no alternative routes left. If the primary pathway stumbles, there is nothing to absorb the shock. Systems slow abruptly. Outputs fluctuate. Corrections lag behind changes. What was once robust becomes exquisitely sensitive to disturbance. Human response accelerates the problem. More controls are added. Feedback loops tighten. Automation replaces judgment. Each layer of control increases complexity while pretending to reduce it. Chemistry adapts to these constraints by finding ever narrower operating windows. The system becomes stable only under perfect conditions. Perfect conditions do not exist. At this stage, warning signs multiply. Maintenance costs rise. Failure rates increase at the margins. Unexpected interactions appear between components that were never meant to interact. Investigations focus on symptoms, not structure, because acknowledging structural dependence would mean admitting that success itself created the risk. This is the emotional peak. The realization that the experiment did not fail because it was wrong, but because it was too right. It solved the problem so completely that it erased flexibility. And without flexibility, chemistry has only one option left: to break the system when conditions inevitably change. The experiment that worked too well has now revealed its true nature. It did not remove uncertainty. It concentrated it. and concentrated uncertainty always releases its energy suddenly. The climax is not collapse. It is exposure. The experiment did not fail because it stopped working. It failed because it worked so completely that it removed every other option. Chemistry was no longer part of system. It was a system. And when chemistry becomes singular, it becomes fragile. This is the final realization. Success that eliminates alternatives creates dependence. Dependence narrows tolerance. Narrow tolerance invites instability. The experiment locked chemistry into one optimal pathway and assumed conditions would remain loyal. They never do. The resolution is not rejection of success. It is respect for diversity. Systems that survive long-term do not rely on perfection. They preserve redundancy. They allow inefficiency. They keep multiple pathways alive. Even when one performs best, chemistry thrives on options. Modern relevance makes this lesson unavoidable. From energy grids to agriculture to digital infrastructure, systems optimized for peak performance dominate the world. But peak performance is not resilience. It is vulnerability disguised as efficiency. And chemistry always reveals that distinction eventually. Once this is understood, progress changes shape. Design shifts from maximizing output to protecting flexibility, from forcing stability to enabling adaptation, from celebrating success to questioning its cost. Because chemistry does not care how impressive a result looks. It only responds to conditions. The experiment that worked too well did not betray science. It completed its lesson. It showed that success without slack is failure waiting for timing, and that the most dangerous outcome in chemistry is not something that breaks, but something that never learns how to bend. Sometimes the smallest shift in perspective becomes the beginning of a new future. The